Log on, tune in, find out. Another good idea from Cambridge.
Well, my name is Walter Bodmer and I'm chairman of the Fisher Memorial Trust, have been for rather longer than I care to remember, and it's a pleasure to host this lecture hosted here. We've been here actually, I think, at least twice before. I just thought I'd say something about the Fisher Memorial Trust. It was set up after R.A. Fisher died. He died in 1962 with the aim of promoting the interest in his life and the work. And as you probably know, he's one of the greatest statisticians that ever lived, evolutionary biologist, founder of population genetics with Sewell Wright and J.B.S. Haldane. And our aim is to maintain that legacy, and we generally alternate statistics and genetics in the major topics of our lectures. And we try and involve them in other activities so they're not freestanding lectures, and we're very grateful to Rosemary Bailey for including it in her program here at the Newton Institute. We usually have lectures on average about once a year, depending on an ad hoc basis on what they can be associated with. Well, today it's a great pleasure to introduce Professor Philip David, who's a Professor of Statistics in Cambridge, as I'm sure most of you know. He previously had chairs at City University, University College London, where he was the Pearson Professor of Statistics. And he's received many awards, the Snedeker Award, Guy Medals of the Royal Statistical Society in bronze and silver. He's the author of many papers and monographs. I better not take too much time up, otherwise I'll take it away from his lecture. But he's, as you will gather, he's internationally renowned for his work. And that's why we're very pleased to have him to give the 30th Fisher Memorial Lecture here. And I can read the title, Causal Inference and Experimental Data. Over to you, Phil.
Thank you very much, Sir Walter. Is this equipment working? Yes. Good. So I would like to express my extreme appreciation to the Fisher Memorial Trust. It's a great honour to be invited to give this Fisher Memorial Lecture, and I'd also like to thank Rosemary and the organisers of the Design and Analysis of Experiments programme here at the Newton Institute, and indeed the Institute itself, for hosting this, which I must confess, when I got the invitation to give this talk, I thought that maybe the Trust had perhaps run a bit low on funds and was trying to minimise its travel expenses. But I'm assured that there was a serious consideration given to flying me up to Edinburgh to give the talk there. But that hasn't happened, so we're here. Causal inference from experimental data. Obviously, I've chosen this because of the concurrent program in design analysis of experiments. Causal inference as well is one of my current research interests. And there's a lot of interest. It's a very big enterprise at the moment, mostly concerned with the rather more complicated problems that arise from non-experimental data, which is incredibly important and convoluted in many ways. But I thought it might be worth taking a step back and thinking about what are the issues when we focus on experimental data. So here's the case. I've actually must confess that preparing this talk has taken a lot of time and effort and given me a bit of a headache. So I've got some aspirin here, but are they going to do me any good? Shall I take the aspirin? What's this got to do with causal inference? I don't know. Well, it just gave me a headache. Anyway, maybe I'll take the aspirin. Maybe I won't. What should I do? So T is the treatment, take 2 aspirin. C is the control, do nothing. I might be interested in how long it will be till this dreadful headache of mine goes away, hopefully before the end of the lecture. Call that Y. And I might measure the loss in some units. The simplest thing will be just how long it takes to go away. It's not particularly important. We won't really focus on that very much. But of course, whether I take the aspirin or whether I don't take the aspirin, I don't know how long it's going to be. I've got uncertainty about how long my headache will last. And being a statistician, I will model that as a random variable. So in either case, I've got randomness, and I want to think about all those ingredients of my problem, and to help me decide which treatment to choose. Shall I take the aspirin or not? I'll leave you on tenterhooks for the moment. Well, being a good Bayesian, I know how to set up a decision tree to help me solve that problem. So here's the story. I start at the left. As you know, trees grow from left to right. And I have two options. I can either take the treatment and move here, or not take the treatment, the control, move down here. When I get to either of these two positions, I look forward to the value of y, how many minutes it will take for my headache to go away, and the resulting loss Ly. There's a whole range of possibilities, of course, and at either of these positions, I'm uncertain about what the value of y is going to be, but with typically a different uncertainty depending on whether I've taken the aspirin or not. So I'd be interested in the distribution, P of t, the distribution of y, should I actually choose to take the aspirin in this position, and here I'm interested in the distribution, P sub c, of the time it will take to go away, should I do nothing. Suppose I could assess those two distributions, and I know the loss function. Bayesian decision theory would tell me that I should choose to take the aspirin if the expected loss under the distribution relevant to taking the aspirin is less than or equal to what it would be under the alternative distribution. And the important point here is that all I need to do to solve this problem for any loss function is to know what these two distributions are. And I call these hypothetical distributions. This is the distribution. So at this point, I haven't decided what to do. I'm trying to solve this problem. On the hypothesis that I were to take aspirin, this will be the relevant distribution. And on the alternative hypothesis that I were not to take the aspirin, C, this will be the relevant distribution. There are two hypothetical distributions which I must consider. So that's about as Bayesian as we're going to get today, as many of you will be pleased to know. But I want to contrast that, what I call the hypothetical approach, with what we might call the counterfactual approach. And this is a philosophical distinction. Some people think it's a distinction without a difference, but I differ on that. I think it's a distinction that makes quite a lot of difference. So the story here is, instead of considering a single variable, namely y, how long my headache will last, but with two hypothetical distributions for two different circumstances, I split that in two, right down the middle, into a variable yt, which is how long my headache will last if I apply the treatment, if I take the aspirin, and another completely separate variable, yc, which is how long it will last if I don't take the treatment. So the one variable has been divided into two. And the conception here is that somehow or other, these, at this point where I haven't even decided what to do, these values nevertheless exist. Both of them exist. And they exist together, and I could in principle assess a joint distribution. It would be a bivariate distribution for these two things. Things are getting a bit more complicated than the simple decision tree, where I only needed univariate distributions. And the conception too is that if I take one of the actions, like if I take the aspirin, what I'm going to do is basically raise the curtain, which currently there's a curtain covering each of these values. I raise the curtain and look at yt, but the one covering yc is still firmly in place, and I can't see what its value is. Alternatively, if I were to choose not to take the aspirin, I'd raise the other curtain and observe yc, and I wouldn't know what yt was. With this understanding, I would have these two different variables. There's a joint distribution, but I would look at the marginal expectation of the loss of yt and compare that with the marginal expectation of the loss of yc. So that looks in a way very similar to what we had before, but the difference is we've split the variable y down the middle, and we're doing rather different things. Now this kind of conception of these potential responses is essentially the state of the art in modern causal inference. Its current popularity is due to Donald Rubin, and he's made tremendous important contributions to causal inference, but one I personally think this is not one of them. We'll come back to it. So throughout this talk there's going to be some sort of comparison of the two different approaches, the hypothetical approach, which has one variable under two hypothesized distributions, and the potential response or counterfactual approach, which has several variables simultaneously existing with a joint distribution. The word counterfactual is used because should I choose to take the treatment, then even thinking about YC, what would happen if I did the other thing, is thinking about a circumstance which is entirely counter to the fact that I actually took the treatment, and therefore I can never observe it anymore. Okay, well, whichever approach we take, it might be a good idea to get a handle on what's really going on, reduce my uncertainty, get some data, estimate distributions. So let's go and think about getting data. And there are two main ways we can get data. We can just go out and look to see what's happening, observational studies, or we can do experimental studies where we set things up and intervene and control things and see what happens there. As I say, most modern work in causal inference is concentrating on observational studies, but here I will concentrate on experimental studies. So what is causal inference from this point of view? It's three things. First, I want to use the data somehow or other, obviously, and what do I want to do with the data? To solve my decision problem, I want to use this data on other individuals who've taken aspirin or not in the past to help me decide what would happen if I were or were not to take aspirin, to predict my outcome. And once I can make that assessment of the two distributions that are relevant, or if you're a potential response kind of person, the joint distribution of the two potential responses, I can use that to solve my decision problem. So data, prediction, decision. That's the story. Okay, now let's suppose I've done a study. How does that relate to my decision problem? So let's think of a simple two-arm, perhaps randomized, controlled clinical trial where there's a treatment group that were given the aspirin, and I got N patients, and these are their successive responses, which I will have observed. And there's a control group who didn't take the aspirin, got all their responses. There's the data. What do I need to know or to do or to assume in order that that's any use to me? Well, I want to use that data to help me assess my predictive distributions. So I'm going to hope that those data are going to be relevant to saying something about these distributions for me, PT, or the distribution of potential response, whether or not I take aspirin. What's required there? Well, let's first of all consider the treatment group. How and when can I use the data from the treatment group to help me assess what would happen if I took aspirin? Well, I might have to consider that in some way I'm like them. Because if I'm completely different from them, forget it. It's too complicated to know how to use it. Maybe there's some modeling I can do. But the simplest assumption is essentially, in using the Bayesian word, which I promise not to use anymore, we could use exchangeability, that there's sort of no real reason to distinguish myself from the mass of patients who already got the treatment. In which case, by means simple or complex, I can use the data from the treatment group to estimate my distribution, get a better handle of it, which is to say I can predict my response Y if I were to take the treatment. Or if you're, again, a potential response person, it says I'm predicting YT. So that's good, but it does require this assumption of exchangeability, otherwise that treatment group data is no use to me. So I've got to be exchangeable with the treatment group. But I also want to assess my distribution if I were not to take the aspirin. So in order for that to be true, or appropriate, or possible, I've got to consider myself exchangeable with the control group. So both of those things have to happen simultaneously. And if I'm exchangeable, if I myself am exchangeable with each group, at least on all the pre-treatment variables, then it's certainly necessary those two groups have to be exchangeable with each other. Otherwise, it couldn't happen in both cases. So, this is one way of justifying why we have to be careful in gathering our data and performing experiments. We must be comparing, the two groups must be comparing like with like, and essentially differing only in the fact that some got the treatment and some did not. And that's why we need all those wonderful things that Fisher made such important contributions to: randomization, blocking, covariates, things which, with sufficient care at both the design and the analysis stage, can make me assume basically that I have the appropriate exchangeability at an appropriate level and can do my comparisons. But without all that, and particularly in the context of observational studies, I can have an awful lot of trouble in justifying using the data to make the appropriate causal inferences. Much easier with experimental studies, but nevertheless, it has to be done and it needs justification. Okay, so let's then think about the process of experimentation. A lot of people here who thought a lot more about this than I have, so my apologies to all the experts here. But the basic idea is to distinguish between the experimental units, the patients, me and all the others like me who are wondering whether or not to take aspirin, or might in the past have taken aspirin or not, or in the future might or might not. And then there are treatments which we could apply. And the basic idea is that the units are pre-existing, but the treatments can be assigned independently of the units. So any unit could in principle receive any treatment. Typically, there are lots of wonderful complications, both in terms of the pragmatics and the mathematics, in terms of complex structures for the treatment set, for example, factorial nested treatments, complex structures of the unit set, in terms of various two-dimensional layouts or split plots and all sorts of things. We introduce blocking, covariates, all the wonderful stuff that design of experiments pay such a lot of attention to. But the essential point is that we can at least conceive of applying any of the available treatments to any of the available units and measuring the associated response. So here's what we're going to do. We're going to collect some set of experimental units, not everybody in the world, but the ones we're going to put in our experiment, or U0. And then we're going to decide to give them some treatment. So some of them will get aspirin, some of them will get no aspirin or whatever. So we have a map which associates with any of the experimental units, one of the members of the treatment set. And probably, if we're being careful, we'll do some randomization, both in the selection of the experimental units we're going to study in the first place and in the way in which we assign the treatments to them. But we've done all that, and we want to assess, compare the effects of the treatment. So we've done the experiment. We want to do causal inference. What for? Well, for my decision problem, ideally. Maybe my decision problem, maybe it's the farmer in Central Africa who wants to use the results of the experiment in Rothamsted, or whatever. But there's no point in doing this really unless it's going to be useful to somebody somewhere sometime. So to help them solve, I don't have to specify now what the decision problem is, but it must be possible to use it to solve such a decision problem. Okay, so let's get a bit more philosophical then. What do we mean by the causal effect of a treatment? That's what I want to understand. Particularly, I want to understand, and so in terms which it relates to me, but also perhaps in terms of which it relates to the units that have actually been experimented on. So so the hypothetical level, and I'm attaching Fisher's name to this, probably taking his name in vain here, but it seems to me that this is roughly the sort of thinking that underlies much of what he did. It's at this hypothetical level where we came in that we consider for each possible treatment I could assign to a unit what hypothetically would be the distribution of the associated response. And for the same unit, I can hypothesize assigning different treatments, and for each such hypothesis, I can think about what the response might be, and it would be random. So in each case, I get the distribution P for each hypothesized treatment T. So as a simplest model, what we might call statistics 101, we might model the the response for the unit U hypothesized on being assigned treatment T, I might model as normal with a mean alpha T, which depends on the treatment, and a variance phi y. So the simplest possible model, and completely unrealistic, and we'll use it all the time, of course. So if my loss function were simply measured by the actual amount of time y that my headache's going to last, I'm interested in comparing the expectation, my expected loss, the expected length of time my headache will last if I take the treatment, and compare that, or take one treatment T, compare that with some other treatment T dashed. That's a causal contrast, and it is basically any comparison between features of these varying different distributions as I vary T. I don't have to compare the means. I could compare the means of the logs or the variances or whatever. It's some kind of comparison between distributions. That's the important point. And we can consider, in this particular simple form, we could say it measures how much longer I expect my headache to last, the difference in the expectations of two distributions, were I to take aspirin compared with taking nothing. And of course, at this simple level, with this model, that difference of expectation is nothing other than the difference between the means here, the parameters, and again, which we would typically focus on our first level statistics course. And in the language of causal inference, this will be called the average causal effect. Fine. And anybody who's done an elementary statistics course and got to the end of it will hopefully recognize how simple all that is. And we have techniques for handling it. That was what I call the hypothetical approach. Seems to me to fit in very well with the Fisherian ideas of design and analysis. But there is an alternative, and that is based on the other version I introduced earlier on, the potential response approach. So I've labeled this with Neyman and Rubin. It almost certainly is ascribable to Neyman originally, I think, almost certainly. And we're going to talk a bit about that. In modern times, Don Rubin has been the person, as I said, who has taken this up in a big way and run with it in causal inference as essentially the fundamental framework for all kinds of causal inference. So the idea here is a bit different, but it's splitting the values, as we did in my simple example earlier on. So for each unit, we imagine we could apply each of the treatments to each of the units. And for each treatment that we apply to that unit, we would measure some response. And they are all, again, supposed to be pre-existing with some multivariate distribution, although, and the effect of actually experimenting on the unit and applying a specific treatment is to lift the curtain covering that one component of this multidimensional vector, which has one component for each treatment. So they're all there, and you can model their whole distribution, but you never get to see more than one of them. If you're lucky, that's if you experiment at all on that unit. Okay, so that's the conception. So we're in the potential response landscape here. And from this point of view, you'd say the causal contrast is not a comparison between features of distributions. It's a comparison between values of responses, actual values. So here U is me. I'm unit U. Here's the value my response will have if I actually take aspirin. And here's the value it will have if I don't. Let's take the difference. That's what that would be interesting. I could say, okay, that's 10 minutes. Maybe it'd be 10 minutes quicker if I do take it'll go away 10 minutes faster if I do take the aspirin than if I don't. And that would be a nice, that is, so it's exactly measuring how much longer or shorter it would last, if I were to take aspirin rather than nothing. And it's something we might call, and is indeed called, the individual causal effect. But it has rather serious problems, which is I can never ever, I might be able to measure one of these things. If I actually took the aspirin, I can measure this. If I didn't, I could measure that. No way I can both take it and not take it, and therefore measure both of them. And therefore measure, the difference is forever unmeasurable, which is a slight problem. Okay, so, but anyway, this counterfactual approach starts by positing that these things do exist, they have joint existence, and we could build a joint distributional model for this collection of values which are supposed to exist all at once, even though no more than one of them can ever be observed. What we actually are going to observe is for the units that do get into the experiment, those in the set U0, and for the treatment which is the one actually applied to that unit, I can observe that. Those are exactly what I observe, but that's a very small subset of everything available. As I said before, we never observe both of these, so we can never observe an individual causal effect. And this is what Paul Holland has termed the fundamental problem of causal inference. There is always missing data. Now, as I said, one of the instigators of this enterprise of potential response modeling in causal inference was Don Rubin. And I like to think, I haven't discussed this with him, that he just very shortly before he did this, he'd done a lot of very fundamental and still very important work on statistical inference with missing data. Nothing to do with causal inference. However, I think that he was so enamored of this, and quite justifiably so, that when he came to think of causal inference, he said, oh, well, really, it's just a problem of missing data. And we have all these things that we can't observe, and the problem is use the theory of missing data, and off we go. We have the technology. Okay, right, now, getting physical and metaphysical at this point, so getting philosophical, certainly. What do I mean by the physical array? If we actually do an experiment, so here's an experiment which is performed with 3 different treatments, and for simplicity, the same number n of patients, if you like, under the 3 different treatments. And these are the observations I can make. So this is a simple one-way layout, analysis of variance type problem, and of course, these are measurements on 3n distinct patients. And I could think of modeling that and looking at the values of them and seeing what inference I could draw. On the other hand, if I were to take the potential response approach, I could complicate things. And here's how I would do it. I would say, well, I've got all these units, some of which I might experiment on and some not, U1 up to UN. And I got the various treatments, and I can do a 2-way array of treatment by unit, because the conception is that for every possible treatment applied to any possible unit, I have a value, the actual response. Of course, these are unknown, but in principle, the idea is we have this 3 by n array of potential values. I call it the metaphysical array for rather poor reasons, really, but basically, you can never observe it all. So if we went back to the physical array, in principle, you can observe all those y's simultaneously. Whereas in this one, you can imagine all of those things exist simultaneously, but it's a logical impossibility to observe them all simultaneously. And in particular, if I focus on a particular unit, I can in fact apply one of the 3 treatments, but no more than one. So there's no way I can actually observe more than one of these 3 values in the column. Well, never mind. Let's assume that all these things are out there. Granted, I can't really get to grips on all of them. What do we want to know? So the conception that comes from Neyman and Rubin is basically it's features of that array which I'm interested in. Those are the objects of inference, essentially. So what I would actually do, the color's not coming out very well. Some of these have turned red, but it's more like a murky brown. So if you look very carefully, eta 1,1 has turned red, as has eta 3,2. That means that I've done that experiment. I've applied treatment 1 to unit 1, so I observe that. I've applied treatment 3 to unit 2, and I observe this. 1 to unit 3, I observe that. I haven't done any, unit n-1 never even got into the experiment. I've observed nothing. I've observed eta 2. So I can observe at most 1, by doing an experiment, 1, possibly none, of the etas in each column. Okay, I can now rearrange those. So if, we don't really need to do the notation, but basically treatment 1 was applied to unit 1, unit 3, treatment 2 was applied to various units up to n, treatment 3 was applied to unit 2 and various others, and I could just put those in the appropriate places, and those are, if you like, the replications of these are all distinct, completely distinct patients, and really I can consider them as corresponding to what I previously called the physical array, the values I could actually all observe. So I got these two different ways of thinking about the problem, the physical and the metaphysical. One involving complete observability, and the other this only very partial observability, but which, as it were, reproduces it. So we can imagine the physical array is a very partial observation on the metaphysical array. So what does that mean? Well, suppose I set up some kind of model, however complex I want it to be, for this metaphysical array. Well, the physical array then, being just a subset of those values, will have an induced model. So any such model induces a model for any observable physical array. I say any observable because there are all sorts of different ways I could apply my treatments to my units, but whichever I do, I would get an appropriate model. But one thing I want to point out, which I think is rather important, is that there is not a one-to-one correspondence. There's so much more information in the metaphysical array, so many more values to model their joint dependence and everything. There are 3n, sorry, there are, yes, how many values have we got? 3 times capital N values in the metaphysical array and 3 times little n, the size of each treatment group in the physical array, and that would be much smaller. So what this means is that different ways I might model the metaphysical array are completely indistinguishable in terms of what they imply when I only look at the things I can observe, the physical array. And we'll come on to examples of that shortly. And the main reason for that is that if I build a model for the metaphysical array, it will include various assumptions about within each unit I can consider all the different responses I personally might have to the different treatments and have a joint distribution for them, and I could assess the correlations and things like that. But whatever I assess, there's no way that dependent structure will be reflected in the physical array because I never get to see more than one value for each unit. So things like correlations among outcomes for the same unit are simply irrelevant to the behavior in the physical array. So what does that mean? Well, one thing you might say that's wonderful because I've got this much greater flexibility, many more models I can build, and many more ways of describing the more complex metaphysical array. Very nice. All right. Good thing? Not so sure. Because as I pointed out, different structurally distinct metaphysical models may have the property that they can never be distinguished. They always imply exactly the same structure for any physical array. So what do we do if we use this wonderful flexibility of modeling the metaphysical array to make different inferences in cases like that? Is that a good thing or a bad thing? There's no way I could tell these models apart, but because they're mathematically distinct, depending on how I process and analyze them, I might, in principle, come to different inferences. It depends on my method of making inferences, of course. Is that right? Yes. So let me try and make that a bit clearer, if I possibly can. Let me just go back to the metaphysical array. So that was the metaphysical array. It's a two-way layout of treatments by units. And we've got all kinds of ways we model two-way layouts. And an obvious thing, we might have a main effect for treatment, a main effect for unit, and an interaction term, for example. Let's go back again. Doesn't work. Okay. Bad. Okay. Right. So there we have it. There's a sort of standard layout with main effect for treatment, main effect for units, and interaction term. And I'm going to just specify rather arbitrarily this model where the alphas are, if you like, fixed effects for treatment. The betas are random effects. Normal means 0. some variance phi beta, and the epsilons are random effects. Normal means 0 variance phi epsilon, and all those random effects are independent of each other. So I can make various choices of the alphas, the phi beta, and the phi epsilon to specify such a model. What does that imply for what I could actually observe, what I've termed the physical array? Well, it's rather trivial to see that if I is the ith replication, the ith unit that gets associated with treatment T, well, the mean is going to be alpha T. There's going to be all these different observations are on distinct units. You can't observe the same unit under two different units. They're all distinct units, and consequently, the terms beta u and epsilon tu for different replicate observations are completely independent of each other. No repetitions there. And therefore, the variance of this is just the sum of the variances, beta and epsilon, and these are all independent. Okay, so that's the physical model. So what I really want to point out there is that the two distinct parameters, phi beta and phi epsilon, which I chose to enter into my metaphysical model, cannot be separated by any observation whatsoever. If I have no prior knowledge of what they might be, I'm certainly not going to gain it by any experiment, because all I will get is observations with variance phi y, and I can estimate their total, but there's no way I can separate that out into individual terms. Implications. Right. Treatment unit additivity. That means what it says. So this is a common assumption that's made in a causal inference, that the interaction terms that I put in aren't actually there. So it's a specific hypothesis. What does it mean? It means that phi epsilon is 0. What does that say about the behavior, the behavior of the epsilons, of the y's rather? Absolutely nothing. All it could, because if that's 0, it can soak it up with the phi beta. There's no way I can look at the data and decide whether treatment unit additivity holds or not. Any data that could conceivably be observed, ever. In particular, it's an utterly untestable hypothesis, and I would regard it, therefore, as completely, well, I don't know if meaningful or meaningless, but certainly pointless. Why do I need it? So the only way I would say that we can really make sense of this state of affairs is that whatever inference method we are tempted to use, we should be sure that it has the property that it doesn't actually depend on whether or not I assume treatment unit additivity. Because why should it depend on a hypothesis which has no effect whatsoever on anything I have observed or ever could observe, and in any case is untestable? So that's my hypothesis, and I ask you to think about it. Right, Neyman. There's anybody who hasn't read this paper and the exchange followed it certainly is advised to do so. 1935 paper read to the Royal Statistical Society by Neyman, with a wonderful discussion including contributions by Fisher. So Neyman works quite explicitly, and apparently he was the first person to think of this metaphysical array, and he's fairly reasonably explicit about it. And he says, what are we interested in testing? We've done, here we are doing, he's talked about agricultural experiments, so we've done an experiment putting fertilizers on plots of land in a field, the usual kind of thing, various different ways we can do that. And he said, what do we care about? Well, he imagines this two-way layout that for each fertilizer you could apply to each plot, there is a hypothetical response. If that's the case, we can say, let's consider all the units in the experiment and say, if I actually were to give them all this particular treatment T, then these would be the actual values I observed. I didn't do that, because I gave some of them one treatment and some another. But if I were to give them all treatment T and take the average over the whole field, that's an interesting, I can say that is somehow the overall level I would expect to get if I applied treatment T. That's a measure of the effect of treatment T. And I can therefore compare it with similar measures for other treatments. So you do comparisons of things like this. The average outcome over all the units which are actually used in the experiment, the actual plots of land in the field that you have applied the fertilizers to. and say what would you expect to get if you did a uniformity trial and gave treatment T to the whole field and looked at the average yield over the whole field. Sounds like a sensible thing to do. Okay. So, but I point out that it's very clearly focused on the metaphysical array, this two-dimensional collection of values. The hypothesis doesn't relate to underlying models or statistical parameters. It's just about the values, some of which, a few of these might actually have been observed, but most of them will not have been. So we're making inference about unobserved quantities, inference about missing data. Another point to make is if I took logs or exponents or other nonlinear functions of these things, if these things were equal on one scale, they would not necessarily be equal on another scale, and therefore it's a hypothesis which clearly is dependent on the particular scale of measurements I'm talking about. And perhaps more to the point, it depends on the field I'm talking about. Depends on the very same plots that I actually used in the experiment. And if my job is to say, okay, here I am, I'm a new plot, wondering what fertilizer to use, how does that help me? Okay, and then of course we still have the fundamental problem of causal inference, that we can never observe both of these, and typically unless we've done a uniformity trial, we won't observe either of them. Okay. But it's interesting what happens to Neyman's null hypothesis if we do make the treatment unit additivity assumption. We find that under that condition, to say the averages of these over all units are the same is equivalent to saying that the alpha t's are all the same, or equivalent to saying that for any unit, the different responses on that unit to the various treatments are all the same. So that's a very strong assumption about the behavior of the metaphysical array. But I point out that it no longer actually depends on the experimental plots. It's either true or false. If I took a subset of them, it would equally remain true. If we go back to this model where the betas maybe come at random, then we have the sort of standard model. And I said before, it didn't matter actually whether we had the epsilons on the end or not. Here we don't. But anyway, we're back to statistics 101 and very simple, straightforward analysis of the problem. So with treatment unit additivity, we can take seriously the first statistics course you ever did and do the things you were taught to do. But that does depend on treatment unit additivity. Without that, we have the more complicated hypothesis you set up, that the averages of hypothetical uniformity trials are identically equal. And so Neyman looked at this in detail. So under his, and he showed that it's not under his null hypothesis. The mean, if you look at the usual mean squares for treatment and for error, which under the sort of standard null hypothesis would be equal in expectation, that's not true for his null hypothesis. If you cannot assume treatment unit additivity, it does seem to be okay for randomized blocks. But it fails for the Latin square, and Neyman decided that the Latin square design is biased. Doesn't do the job. Well, unless you can assume TUA, treatment unit additivity. So but how do we know whether we can assume it or not? Nothing we can observe will help us decide. So there's a slight problem there. We actually get different answers now, depending on whether we can or cannot assume treatment unit additivity. So this analysis is in violation of the precept I suggested earlier, that if models are indistinguishable about anything they could say about anything you could ever observe, they should not lead to different inferences. If we use Neyman's null hypothesis, that's violated. There's a lot of work on this, particularly in the 50s. Won't go through it. Wilken Kempthorne in particular, extended, corrected, did lots of analysis for other layouts. Right, so that was Neyman's paper, and then comes the report of the discussion. And it's wonderful reading. And Fisher, who's noted for his rudeness on all kinds of occasions, really excelled himself on this one. And I've expurgated it rather. I'm going to choose some of the milder comments that he made. He pointed to Neyman's apparent inability to grasp the very simple argument by which the unbiased character of the test of significance might be demonstrated, and that the sole source of his statement about that the Latin square design was biased appears to lie in the peculiarity of his own notation. So that was nice. So Fisher laid into Neyman, and basically, well, it's always difficult to interpret Fisher, a bit like the Delphic oracle, but certainly was worth trying. But he clearly didn't see, he didn't really like this idea of the metaphysical layout, I think. To be fair, Fisher has been criticized in the same way. So, in particular, in 2004, some of you will know there's a rival Fisher lecture series, which is organized by the Committee of Presidents of Statistical Societies in the United States, also a very eminent lecture series. So, Don Rubin gave one in 2004, which he pointed out correctly that Fisher never used the potential outcome framework originally proposed by Neyman. As a result, he provided generally flawed advice concerning the use of analysis of covariance. I mean, that's in the context of a very special problem, and I actually think that possibly, I won't say definitely, possibly Rubin actually has a point there, that maybe he did provide somewhat flawed advice, but I don't think Rubin's advice actually is any better. So it's not clear that potential outcomes are going to help. Okay. What was Fisher's version of the null hypothesis? In words, the treatments are wholly without effect. What does that mean? So we have to decipher the Delphic oracle. Difficult. Various different proposals have been made. One that refers to the metaphysical array. It says that, and it is the statement that for any unit, the potential responses you might have to all the different treatments are identical. Another is, if you like, physical, refers to the distribution of the observable data, and it's although we've labeled these with some treatment indicators, they're completely irrelevant, and the joint uncertainty or distribution for the y's doesn't depend on them in any way. I'll make that a bit more explicit perhaps in a moment. And David Cox, I hope, won't mind me completely misinterpreting his 1958 paper as saying that the null hypothesis should be that the variation between the observed treatment means is consistent with sampling for a homogeneous group of observations. And I think that's a paper I like very much, actually, for its good mixture of common sense and analysis. Anyway, these are sort of different paraphrases of the same thing, if you like, and you could use any one of those to justify your Statistics 101 analysis of variance and permutation tests. And so Fisher said, the Latin square design is unbiased for the test for which we should be, the hypothesis we should be testing, which expressed in one way or another is one of those things. Okay, now I took this up several years ago, and in terms of this idea of basically, what do we care about and what do we not care about, what I call symmetry modeling, thinking about the ways you might permute the order in which you look at the data and analyze the data and whether they make a difference to what you think or not. So we think about this, we're getting into the theory of groups of permutations. The main area in which this has been very heavily researched, particularly by Rosemary here and from many others here, is in the randomization theory of experimentation. I like to think of it in a more subjectivist approach of Bayesian exchangeability, but the basic principles are the same. To say that I don't care if I permuted the data in some way is a property which won't be changed if I take logs. So that's nice, independent of the scale of measurement. It doesn't depend on anything like treatment unit additivity. And we can now get a bit of maths in it. I'm not going to give you much maths, but you can actually get into some quite deep algebra and with group representation theory. In particular, quite simply, you can use this to structure the way in which the covariances between observations, be they say for the same or different treatments, are connected. We can build something which looks like a linear model, called a population linear model, and we can use the group theory to tell us exactly how we decompose the data into uncorrelated strata and therefore can do things like analysis of variance tests. So that's all very neat. And I like to think, what is the null hypothesis? Going back to the idea that the treatments are without effect, we say, well, I don't care. I can permute the values in a way which actually doesn't pay any attention to the treatment label. So that will be a bigger group of permutations I'm allowed to do than if I did have to pay attention. So I think of a null hypothesis as saying there's more symmetry than you first thought of. So we can do this at both the metaphysical and the physical level actually, but we'll stick to the physical. So here's our physical array, and just for simplicity I'm going to assume that not only, what is very reasonable is we assume that if I were to permute in any in any row, if I were to permute the n different values and put them in a different order, you probably wouldn't care. The analysis wouldn't take account of the order they came in, and I could do that separately in the second row and separately in the third row. And also this might be less realistic, but I might say these are 3 different treatments I've never seen before in my life. I've got no reason to distinguish between them. So looking ahead to what I might see, I could actually put the whole rows, the 3 rows, shuffle into a different order, and I'd think the same thing about them. I still take account of which are in the same treatment and which are different, but otherwise I've got exchangeability of the treatments. We can drop that, but it just simplifies life. So the form model says that we can permute the treatments, these 3 rows wholesale, and within any row we can permute quite separately the indicator of the replication I. So there's a nested structure, the replicate I within treatment C, and I put a twiddle on the top to denote that I can do appropriate permutations on those without changing anything. Symmetry. The null model says I've got 3 n values here. The fact that they're separated into 3 separate rows is thoroughly irrelevant. I could, if I've took those 3 n values and rearranged them with an arbitrary permutation and plonk them down again, that would be just as good. If there's no difference between the treatments, surely I can do that. So we might say this is the joint cross-classification, not a cross-classification, the joint set of all the 3 n values, t dot I if you like, with completely random. Well, we can do lots of things with that. We can specify what that says about the nature of the covariances between, and it depends, the covariance between 2 values will depend on whether or not they have the same treatment, and if they have the same treatment, whether or not they're on the same unit. And that's it. That's not surprising. And the null model, which says I've got full permutation symmetry, it can be regarded as specialization of that, where gamma t is gamma u. Because the treatment, the extra component due to treatments doesn't make a difference. We can also describe that covariance structure synthetically in terms of a model which is a completely random model with, these might or might not be normal, so I haven't put a distribution indicator, but the mean and the variance of these things, all uncorrelated. That's the kind of model we're happy to see for analyzing that kind of one-way layout, particularly in the random effect terms. And the null model it says that the alphas aren't there, which again is completely natural and is completely equivalent to the earlier description in terms of covariances. And then we can look at the data. By the way, I did just point out this, that both this and the previous slide on the covariances, these are models which don't have anything to do with the particular size of the array you experimented on. It's just pairs of variables and how they relate to each other, essentially. The data decomposition does depend on the structure of the data. So we're taking averages, overall averages, treatment averages and things in the way we're used to for analysis of variance decompositions. But the point is that we don't have to have wonderful insight to write this particular equation down. It comes out of the group theory, group representation theory, tells us that this is the appropriate decomposition for that permutation model. It also tells us that the appropriate decomposition for the model where I could permute all the values, it has only these 2 components. So what does it say? It says that what were previously 2 separate strata, if you like, 2 separate components of the decomposition, are actually combined into 1. That can only happen if the mean square in each case is the same. So the null hypothesis is indeed the equality of expected mean squares, which is the standard null hypothesis, and which is in turn equivalent to the previous formulation in terms of the population linear model. which in turn is equivalent to the previous formulation in terms of covariances. They're all different ways of saying the same thing, but hey presto, right away the maths tells us what to do. We test for the equality of mean squares for these two different strata, and assuming normality, we know what to do. There's an F-test, so it just pops out. And even without assuming normality, it tells us the sort of appropriate permutation test to do, and it's well known that it's approximately an F-test anyway, and there are good reasons for that. Okay, I must be careful not to overstep my time, so I won't go through all the rest of the material. I'll just quickly point out that we can use these models for the correct task of prediction. The various things we could predict. So we have maybe a more complicated experiment in which various workers work on various machines, each producing a collection of runs for each combination for a lot of widgets. And we have this is the relevant model now. And depending on what we want to predict, let's see, suppose we want to predict, we're going to use one of the old machines that was already been in the experiment, but assign a new worker, and not surprisingly, we want to estimate the mean and the alpha, the machine effect, because we've seen that already, but all the other effects are new, they're random, so it's the variances we need to estimate there, but it tells us what we need to do. All this, the group theory extends rather neatly, and again, Rosary and others have done splendid work on describing this in terms of balanced poset distributed block structures under this full symmetry assumption, where even the treatments can be permuted. If you don't like that, you can take away that symmetry, restricted symmetry. The general approach applies, but the details are rather more gory, and I'll just leave that for you to look at, because I'm not going to tell you the details. What I will tell you is just this, that if I had the previous model but said the machines are actually all different, I know something, I can't assume they're all exchangeable, but the workers are all exchangeable, of course, they're just ideal workers, and the widgets are all exchangeable, then the application of the general theory gives me this model, which I think is rather distinct from any other model we see for what we might call the mixed model. There's for each machine, there's a vector of mu's, one component for each worker. Sorry, I beg your pardon. No, that's wrong. Sorry, this is one vector with one component for each machine. So that's picking out an element of that. These are a lot of vectors and correlated across different workers. And I pick out the appropriate machine component for that one, and then there are lots of random errors tacked on with variances which could depend on what machine. This is just pops out of the maths, and because mu is entirely unstructured, I can say here we've got a mixed model with some fixed effects and some random effects, and we could there are all sorts of null hypotheses we could look at, which I'm not going to go into, but merely point out that for the full model and for any one of the null hypotheses I care about, the group theory tells me the data decomposition. Comparing those data decompositions tells me what statistics to look at and what hypotheses I'm testing. Okay, so I've used up my time, and luckily I've come to the end of my presentation. Brief conclusions. For causal inference and experimentation, I would argue that it really is important to think about the problems of down the line of decision and prediction for what's going to happen next. What are you going to do next? What do you want to know next? I also think that the counterfactual or potential response framework is unhelpful and sometimes positively misleading, and I would urge you to think in Fisherian fashion, which I hope goes down well with the Fisher Memorial Trust. For building models and hypotheses, I would say, but this is a somewhat more personalistic view, way to do that is think about the structure of attitudes to the data and let the models and the tests just come out in the wash. Thank you very much.
Thank you very much for that lecture, and it does finish on time, so I think you'll have to ask questions during the session afterwards. But it's our usual custom to give the lecturer something and we used to have a bowl made by a very famous silversmith. We've still got a bowl. I hope I haven't left the tip. I stick it in. So there is a silver bowl. It should have your name engraved on it. And there's a bag you can have. Whether you'd like to open it.
I would indeed, yes, yes.
Show the audience what it is.
Thank you. Well, this is a great bonus and a great pleasure. Thank you very much.
There is a cheque as well, but we have a little contretemps with our treasurer, so you'll get the cheque sent to you in the post.
I've heard that before.
We promise it'll come.
Wonderful.
You still didn't tell us though whether you took that aspirin. How long your headache lasted.
Oh, the exhilaration of giving the talk has been
Is that what they call the placebo?
I think so. Oh, this is a bit like pass the parcel, right. It is very beautiful. Oh, isn't that wonderful?
Multi-Norrington, I'm afraid.
That is, you didn't tell me that, but I shall nevertheless treasure it with tremendous gratitude. Thank you very much.
Thank you again.
We're going to have a reception outside, yes.
Outside here,
Yeah.
for everybody. Thank you.